So today we're going to start with random variables. So I'm sure like everyone know what the definition of random variable is. So if you have omega and f a measurable space, can anyone tell me what the definition of a random variable is?
A function from the sample space to the reals.
Yes, a function from the sample space.
A measurable function from sample space to the real.
Oh,
to
sorry.
the reals. Whoops. Yes. And it's measurable, right? So I hope you guys remember what the definition of measurable was.
What's the definition of measurable?
Pre-image of a measurable set is measurable.
Cool beans.
So it's in F. So recall this is called the sample space. It's just an arbitrary set, right? And F is a sigma algebra, so called the event space. Okay, just a reminder. Okay, so let's move on to like an example of a random variable. So like imagine like you want to model coin tosses, right? So an infinite number of coin tosses, like in succession, for example, then you would take your omega to be, well, all possible sequences of heads or tails, and I'll use this notation to denote sequences. And what would F be in this case? Any suggestions?
Sigma algebra generated by all these sequences, singleton sets.
Not
No.
quite. Well, you could do a power set, but it wouldn't have really like nice properties. I guess it's a bit too big. So one example would be if you take a sigma algebra generated by this set. So the nth toss you get a head, right? So the set of sequences such that the nth toss is a head. So you take the sigma algebra generated by that, or it's actually equivalent to if you include both heads or tails. So, whoops, this is over n, and yeah. Okay, so example of a random variable would be, let's say x is 1 if the nth toss is heads and 0 otherwise if it's tails. Okay. So why is this a random variable? Anyone?
It's a function from the sample space, and it's measurable.
Why is it measurable?
And the pre-image is in sigma algebra for 1 and 0.
Yes. Okay. Okay. Good. Then, any questions so far?
I'm happy.
Okay. Let's introduce something called the sigma algebra. So let's say you have a collection of functions, y, a collection of functions, just any collection of functions from sigma to r, and you want all of them to be measurable. So you want to find f such that all of these yi's are measurable. Okay, so for that we introduce this. So we want something like small. You want to include the minimal amount of measurable sets possible. So this is called the sigma algebra generated by this collection of functions. Okay, so I is over an index set. So you have this will be denoted by y equals sigma of yi, such that I is in this index set. So what should it be? So this is just notation. So what should be in this y?
You take each yi and look at the preimage of that function in the Borel sigma algebra.
Yeah.
And you do
Yeah.
intersection of all those i's.
You want the
Or
union, right? Union, and
Yeah.
you want to take. So this is actually equal to. Yeah, exactly what you said. So. Whoops. So we take the preimage. So it's like this thing here, such that B is in the Borel. Well, okay, this is the Borel sigma algebra, right? And I is in that index set. So you take the collection of these sets and you find the sigma algebra, which contains all of them, like a small one, the sigma algebra generated by them. Okay, so that's the definition. Let's see what's next. So distribution functions. So I'll define what a law is. The law of, so if x is a random variable, the law of x is the function Lx from the Borel sigma algebra to the interval 0, 1, the closed interval, defined by this. Lx is the composition of the probability measure and the x inverse, the preimage. So if you want to look at this pictorially, so x inverse takes the elements of the Borel sigma algebra to takes the measurable sets to like your sigma algebra f, right? And the probability measure takes f to some number between 0 and 1. Okay, so let's look at like, I guess, a theorem, a small example. So L is actually a probability measure. On the measurable space RB. Okay. So how would you prove that? Yeah. So this is the definition. So what is a probability measure? Anyone?
A measure that maps the sample space to 1.
Yes. Okay. So what do you have to check for a measure?
Oh wait. This is 3 axioms, right?
Sigma additivity.
Yeah.
Yeah. Let's do sigma additivity first. So anyone wants to try?
This is in Math 4005, question
Yes.
question 1 something.
Suggestions? How do we start?
So do we just check the axioms?
Yeah, exactly.
So it maps the empty set, or it maps sigma to 1. Omega, or whatever.
Omega. This goes to 1 because. Wait, is this right? No, right? This should not R because it's a measure on R. So yeah.
Yeah.
I mean, yeah. Okay, so this, the preimage of R is just the entire of. So what does X go to?
That's all of omega. That's probability of all of omega.
It's all of omega, right? So this is just 1, so that's fine. and sigma additivity. So how do you check sigma additivity?
You take you take a sequence of pairwise disjoint sets and
Okay. And wait, is this obvious or should I just skip this?
I mean, yeah.
Wait, so it's obvious?
I don't know. I guess just check it for good measure.
Okay, sure. So disjoint, then okay, so let's check that x inverse bi and x inverse bj are also disjoint. Right. Why are they disjoint? For I not equal to j, of course. Right, so this is equal to and this is empty. So this is empty. And therefore L x of the union is equal to definition is P x union bi. Oops,
x inverse.
Right.
Yeah,
Okay.
because inverse
and-
map, conserves all the set, algebra. That's why.
Yep.
All this
Okay.
is true.
So and this is because P itself is sigma additive, and therefore you have Okay. So is that clear?
Yeah.
Okay. Let's move on then. Okay, what's the distribution function? So the distribution function of x, you can define it by you can define in terms of the law. So you can define like this. Right. So just check the definitions that this actually works. So yeah, this is the same distribution function we're all familiar with. Okay. So the properties of the distribution function. So there are three like defining properties of the distribution function. So one of them is that if f is a distribution function, then it's increasing. So if x less than equal to y, then f of x is less than equal to f of y. Do I have to prove this? Anyone?
I think we did this in Math 4005.
Okay, so
But-
so can I just skip all the proofs of this? Yeah, it's essentially the same. So I'll just write it out so that
Yeah, it might be
everyone's-
worthwhile skipping the proof because you can also take these three as axiom and work that way as well.
And the proofs are on the Berard's lecture notes, I think.
Yes, they're also in the book. And I mean, okay, they're not in the book. Well, it's not too difficult, and it's right continuous.
Yeah.
Okay, so these are like the defining properties. So if you have these three properties, then you can define a probability. Wait, you can define the distribution function. Okay, so we'll look into that next. So if you have a function f which satisfies these three properties, we'll find a random variable such that it has this distribution function. So if f satisfies 1, 2, 3, then there exists some random variable x with this distribution function. Okay, so let's prove that. Any suggestions on what should x be? So let's say we have a distribution function f. Let's like plot it out. So it might look, so if, actually, wait, let me just write a few more things first. So we want to find x which satisfies p of x less equal to c equals to f of c, right? For all c. That's what it means to have that distribution function. So what is this equivalent to? So this is the set of omega such that x of omega is less equal to c, and this thing here is actually equal to p of omega such that omega is less equal to f of c. Is that clear to everyone? Hello?
Let's see.
Sorry?
I think so, but let's see. Oh wait.
So why? Because, oh, wait, right. By the way, yeah, maybe I should just write out a few more assumptions first. Sorry. Yeah, so x, right, we need to know what omega is, like what the sample space we're going to take is. So we'll take the sample space to be this for simplicity, and we'll take the event space to be the Borel sigma algebra on like this interval, right? And the measure will be the Lebesgue measure. So at least this part is clear, right?
Yeah.
And this is because, okay, if we assume this, then do you see why this is true? Because this is like the interval 0 to.
Oh, yeah.
Okay, sorry for confusion. Yeah. Okay, so this suggests that we try to make these two sets equal, right? So if we can make these two sets equal, then we can find, and we can solve for x, then we can find the distribution function. We can find what x is, right? If sort of solve for x by making these two sets equal. So let's try to make these sets equal. In other words, for all omega, x of omega is less equal to c if and only if omega is less equal to f of c. So if we have this, then these two sets will be equal. So we'll have, we'll have x, right? If we can find x satisfying this. Is that okay? Okay, so let's assume that f is continuous and it's strictly increasing. Then what can x be? So assume it's strictly increasing and continuous. Then we can actually take x to be f inverse, right? So it has an inverse, and it will actually satisfy this. But otherwise,
Yeah, but why is f strictly increasing?
that's an assumption. If
okay.
f is strictly increasing, okay. So, but in general, yeah, f is not strictly increasing or continuous. So, okay, let's like look at a picture of what we should take x to be for at omega. So 1, 0. This is a plot of f of x, for example. Okay, so let's say this is f of x. This is a plot of f of x. And what do we actually want here? So let's say omega is less equal to f of c. So let's say omega is like actually, let me simplify this a bit. So if it's like strictly increasing, then if omega is here, what should we take x of omega to be? So that this inequality will hold. Any guesses? So we're trying to solve for x of omega, and we know that f of x is strictly increasing.
The value on the x-axis.
Yes, that is a good guess. And yeah, we can take x of omega to be this. So we sort of like, we want the sort of inverse, right? Okay, but in general, it's not injective, right? So you can't find an inverse. So
Yes. So if you got multiple values, then we can simply choose one of the value from the range where it's stationary. Would that work?
Yes. Let's say there's a line here,
Yeah.
and so we can choose. So let's say this is omega. So we can choose any point here. So there are like two particular points we can choose, like the endpoints, right? So in all of this, C is fixed, by the way. So okay, if that's not clear. So what is, so let's define this to be x minus of omega, and let's define this to be x plus of omega. So what, can you like give a formula for x minus of omega? So if you look to this side, so this is the side. So for all x greater than, so this way.
Infimum and supremum of pre-image. Would that work?
Pre-image. Yes, actually. So so for everything on this side is satisfies f of x greater than or equal to omega, right?
Yeah.
Okay, so we want to take the smallest one, which is this thing. So we can take this to be the infimum. This is actually infimum of x such that f of x is greater than or equal to omega. And similarly, everything greater than this part satisfies f of x is greater than omega. Like if you exclude this border, so you can take x plus to be the infimum of x such that f of x is strictly greater than omega. Yeah. Okay, so let's prove that this actually works. So we want to prove, where's that thing? Yeah, we want to prove this. Right. So let's show that it actually works. Wait, before I move on, are there any questions so far? Yeah, it might be very confusing. Any questions? Okay. So let's check that this actually works. Okay, let's prove the easy way first. So assume omega is less than or equal to f of c. Prove that x minus of omega is less than or equal to c. So any suggestions? Okay, so if you look at the definition, right, and if you just compare this, so C is actually in this set. Right?
Yeah.
Okay, and therefore C is at least the infimum of this set. Wait, this is sorry. Yeah, and this is by definition x minus of omega. Okay, so that was not difficult. So let's look at the other way. So assume x minus omega is less equal to c. Then can you show that omega is less equal to f of c? Oops. Okay, so omega. So let's do this. So let's use this inequality. So we'll show that omega is less equal to f of x minus omega, and it's less equal to f. So this follows from this, right? So since f is monotonic, this inequality follows from this, and we're left to show like this part. So show that omega is less equal to f of x minus omega. And here we have to use the right continuity. So if so we look at something that's greater than x minus omega, then f of z is greater or equal to omega. Can you see why? Anyone?
Isn't this by construction?
Yes. Okay. And therefore, if you take z going to x minus of omega, then you'll get your result. Is that clear?
Yeah, makes sense.
So you should just take z going down to, so it's by right continuity. If you take z going down to x minus omega, then
Yeah, just one question. So the whole purpose of doing all this is to make sure that our theory of, distribution function is not vacuous, right? So there's something that is that exists.
I mean, this is like, given the distribution function, can you find a random variable with that distribution function?
Yeah.
So that's the whole point of this.
Okay.
But you usually won't have to use this. Like, yeah.
Yeah.
Okay, so I guess I should move on. So x plus also has the same distribution function. And do I have time to prove this? Okay. Or should I just move on really quickly?
I think you can use up to 15 to 20 minutes. 15 more minutes. Because I'll also have to show something. Yeah, sorry.
Okay, actually, just let me complete like this last part, then I'll probably be done. Just let me finish this proof. So let's show that x plus also has this distribution function. So just to recall, right? Oops. Okay. So we claim that this also has the same distribution function f, and in fact, p of the probability of x plus being equal to x minus is equal to 1. So they're equal almost everywhere, basically. Okay, so let's prove this. So if omega is less than f of c, so it's sort of similar to what we're doing above, then c is an element of this set, and therefore c is greater than or equal to the infimum of the set, which is this x plus omega by definition. Okay, so this implies that for all c, we have this set inclusion. Okay, so if you take like the probability measure on both sides, you'll find that the probability of this is just f of c as before. This is less equal to the probability of x plus less equal to c. Okay, and okay, now let's show this first. So you can show that the probability that they're not equal is equal to 0, right? But what is this set? This set is, so if two numbers are not equal, right, then there is a rational number between them. So we'll use that. So rational numbers are countable, and that's why we sort of use this trick. So I'm just expanding the definition here. And also note that x minus of omega is always less equal to x plus. Also by construction, I guess, or you could prove that quite easily. And this thing you can write as a union over all of these rationals. All right, so if you want to shorten this, this is just any questions so far?
Oh wow.
Hmm?
It follows so nicely from here, doesn't it?
Yeah. Okay, so we want to show that the probability of this thing is 0, right? So if we can show that each of these have probability 0, it will be done, and which is what I will show now. This is equal to p of x minus less equal to c minus p of x plus less equal to c, right? And this we've proven earlier. This is f of c, and above we show that this thing is we've shown this inequality. So
yeah, that has to be greater than or equal to c, and probability measure can't be negative, so that has to be f of c.
Yeah, so we have this inequality, so this is 0, and therefore this thing here is 0, and so yeah, we've proven this, that the probability they're not equal is 0. Okay, now
well, we have used the fact that countable union of things of measure 0 is also measure 0.
Yes. Is everyone else following along? Okay, so
Q is countable. Yes.
okay. So what was the other thing we're going to show? That
generative
f
sigma.
is also.
Oh yeah, you're right.
No, f is also the probability measure of. I mean, the distribution function of x plus. So this is not too difficult, I guess. So it follows from this. And so this is the distribution function which we want, and we know we've shown above that this is 0. This is for all c in R. This will hold. This is 0. So this we've shown this is 0, and this is f of c. And so we have the result we want. We've shown that this thing is also equal to f of c. Okay, so that's basically it. Okay, I'll pass it over to you now.
Ming, before you go on,
Yes.
could you
Yeah, question.
quickly define what? Could you quickly show what a pi system for sigma algebra generated by a single random variable would be? If not, then I can do that myself.
Wait, what?
A generated
Uh,
sigma algebras.
Sorry?
Could you define? Are you going to do 3.13?
Should I do 3.13?
It's up to you.
Can I skip it?
Oh, okay.
Is it important for what you're going to talk about?
There's one thing I'm going to mention it myself. Thank you.
Okay, I guess you can mention it then.
Yeah. So
Okay.
a round of applause for Ming for giving this lecture.
Okay.
Oh, why?
Okay. So let me get my setup up. So it's going to up. That's okay. At least there were a lot of people here, so there aren't that many absent, I suppose. Share that one. Okay, am I live?
Yes.
Wonderful.
I can see.
Cool. So today we're going to talk about independence. It's not 4th of July yet, but
4th of July, what's that?
America.
those people who are in USA would know. Okay, so independence is defined for many things. It's defined for random variables, it's defined for sigma algebras, it's defined for a lot of things, and they all are similar definitions and they follow from one another. So the first thing to do, the best approach to define independence would be to define in terms of sigma algebras, because that way we can avoid most confusion. And a couple of things that were a couple of loopholes in our first year probability course might also be fulfilled by this definition of independence. So for sigma algebras. Now, so given a sigma algebra, a sub-sigma algebra, a sub-sigma algebra would be a sigma algebra, which is a subset of the parent sigma algebra. So suppose G1 and G2, you can define this for finitely many things, but it is also true for the way we define it. We'll be defining it for infinitely many things. Yeah, but we'll use the finite condition, as you will see in a moment. So they are independent. So these are all sub-sigma algebras of F. So they are independent if we will know the definition, probability of G1 intersection Gn. So we are doing finitely many things here, but this will be true for all n. So if that is equal to the product and a probability of Gn, so for all Gi in Gi, so this Gi is the sub-sigma algebra, and this is the sigma algebra. So as you might remember, a sigma algebra is not, it is a set, but it's a set of sets. So these GIs are in sigma algebra. So the way we find, so given this sigma algebra which has got different sets there, another sigma algebra which has got different sets here. So we call these two sigma algebras different, I mean independent, if this formula is true for example, you could take this set from here and you could take this set from here, and then this formula would be true. The probability of this happening and that happening would be the product of the probabilities of each individually happening. So no matter which set you take from this G1 and this G2. So it's stronger definition than what we were defining the first year. Is that clear to everyone? Am I even audible?
Yeah,
Oh,
you are.
so
you
you're
are.
defining independence for sigma algebras
Yeah,
and not random variables.
yeah.
Okay.
So for random variables, we'll be defining in terms of sigma algebra as well. Independent. So independent random variables. So just as a reminder to the newcomers today, a random variable, I mean, it was done a while ago, so a random variable is a function, is a measurable function from sigma algebra to real numbers. So you take any set in sigma algebra, and then it assigns a real variable value to this. So it's a measurable function. So x1, so given sets of random variable, a sequence of random variable, we call them independent if the sigma algebra generated by that random variable. What on earth could sigma algebra generated by a random variable be? Would anyone like to guess? Independent. Independent. No volunteers? Okay, so I'm so confused when so everyone is so silent, and I'm worrying if my system is working fine or not.
I have no idea.
Cool.
Yeah, it's
So
fine. We just have no suggestions.
okay, so the sigma algebra generated by a random variable would be, so for example, if y is a random variable, sigma of y would be the pre-image of the Borel sigma algebra. This isn't that illuminating, so this would be a set of all sets
Oh,
omega is in B, such that B is in Borel sigma algebra. So you look at all the pre-images of every single set in the Borel sigma algebra.
yes. Okay.
Does this definition make sense?
Yeah.
Wait, isn't that the same with what I defined, but only for a single one?
Yeah, yeah,
Oh, okay. If you mean, yeah, sure.
yeah. For random variable, it should be the sigma algebra for the entire thing. Okay. So that being said, so we have defined independence for sigma algebras. We have also defined in terms of random variables. Let's define the independence for events.
Wait, do you mean sigma of that?
Which one?
Second line of your equation, I guess. You mean sigma of
Yeah,
that?
you're right. Yeah, you're right. You want the minimal one.
Yeah.
Yeah, but if you look at it, this would automatically be sigma algebra. You won't have to add anything.
Oh, right. Okay. Just we're done.
Okay.
Because we're taking every single set in Borel sigma algebra.
Okay.
Independent events. So could anyone remind me what an event is? And what about someone who hasn't
Oh, yeah.
taken lecture 1 and 2, define what an event is?
Wait. So it's either Leos or Simeon, I think.
Okay. So if you guys remember, we had a probability triple. So we had got omega, we had got f, and we got a probability measure on that. So from math 40,005, I believe. Yeah. So what is an event given this?
An element of F.
Yeah.
I mean, you
You're
went to like
Yeah, you're right. So So suppose you've got a sequence of events, E1, E2, and so on. So we say they are independent. Independent if sigma algebra generated by E1, sigma algebra generated by E2, they are independent. Okay, what do I mean by sigma algebra generated by E1? So that's just this. So you want E1 and you want everything else to make a sigma algebra. That's this. Now, so do you guys remember what an indicator function is?
Yes.
Yes.
Yeah. 0, 1, 0 if omega not in E, 1 if omega in E. Yeah. So, if I'm going to write something, and let's see, tell me if that makes sense. Does this make sense?
E1. Sigma I.
Yeah, E1.
Yeah.
So indicator function is 1 if omega is in E, 0 if omega is not in E. So sigma generated, so it's sigma algebra of I of E1. You would be looking at the pre-images, right? So pre-image
Yes.
of 0 would be E complement. The pre-image of 1 would be E,
Oh.
and you'd be adding pi and omega to make it.
Oh, right, because E1 is a set, and so use a normal one. But then because IE1 is a random variable, you have to use.
Yeah,
Okay, right. You have to use the different definition.
yeah. So if that is the case, then we can say that E1, E2, etc. are independent if and only if these functions, these random variables, I of E1, I of E2, etc. are. Okay. Now, these sigma algebras are quite nice theoretically, but they aren't practical in terms of use. So sigma algebras are hard to use, and there are different things which are not quite sigma algebra, but which are known as pi systems, which are easy to work with. So we would like to work with pi systems. So a pi system is a system. It's a non-empty system. So sigma algebra has 3 definitions, so 3 conditions. Pi system has only got 1 condition. It is closed under finite intersection. So we would like to work with pi systems. Okay, so yes, a lemma. So suppose G and H are sub-sigma algebras. Sub-sigma algebra of F. And so let me write some kind of, this is a cursive I. So I and J, so they are pi systems. Systems such that pi of, they are pi systems such that the sigma algebra generated by them by I is G, and sigma algebra generated by J is H. And then G and H are independent if and only if and only if the pi systems are. So this is quite a powerful result, and it's not difficult to prove, but it might be difficult to understand to get a a feeling of them if you haven't done problem sheet 1. So I would like to put one question in problem sheet 3 so that you'll get some practice with pi system. Proof. Let me show you the full screen. Let me make it smaller. Is that big enough for you guys to see?
Yeah.
Yeah, that's fine.
Cool. Okay, so it is if and only if statement. That means we have two things to prove. But if you guys remember the definition for independence of sigma algebra from 2 minutes ago, then you will notice that sigma algebras are independent if and only so if you take no matter which set you take from those two sigma algebras, those are independent. So one way is trivial from this because so I is a subset of G and J is a subset of H. So one way is easy. So if G and H are independent, then surely I and J are. However, suppose I and J are independent. Okay, I didn't want to use too many letters, so let me use one more I, so that will be clearer. So fix I belongs to I. Then let me use small I and this I to denote, just kidding. So you want to fix this I, regular I in this cursive I. Then you want to define, so you want to define a function from H. So mu of H. So for a function in H, so you want to define, so for H in H, so you want to define a measure on H. So H to R defined by mu of H. I intersection H, mu1 and mu2. P of H. So for all H in H. So this regular H is just a set in H, and the cursive H is the sigma algebra. So what we'd like to show is to show that these two things, they are equal. So these two measures are equal. Now, these two measures, they agree in J, because I and J are independent, right? And since H is a sigma algebra generated by this pi system, so from our extension theorem, what's it called, Kara-Theodori extension theorem?
Kara-Theodor, yeah, you got it right, yeah.
Yeah. So from our extension theorem, these two measures should agree on the entire H sigma algebra generated by the pi system. So P of I intersection H equals P of I times P of H for all I in the pi system and H in the sigma algebra. But this isn't enough, is it? So we have only shown that I and H are independent. What we want to show is that G and H are independent, but that's, you can apply the same step again, and G and H are independent. I think understanding the result is more important than understanding the nitty-gritty of the proof. But if you want to do the proof, then it is only one more line. So you define it the same way, and then use Kara-Theodori extension again, but this time on I. Okay, so from problem sheet 3, everyone has seen that, right?
Wait, Promise 3? I don't think I have that.
Is
Yeah,
it
it's going
even
to come
out?
out tonight. It's going to come out
Oh.
tonight.
Okay.
Okay, so since I told you that I'm going to put some questions regarding pi systems, so one question there would be a pi system, one of the pi system for. So suppose Y is a sigma algebra. Yeah, I will give you a pi system such that sigma Y would be the sigma algebra generated by that pi system. And that pi system is going to look like the following. Pi of Y would be defined to be omega such that Y of omega less than or equal to x. Oh, since we're already running out of the time, so I'm only going to take 5 more minutes for you guys. So I'm sorry for taking slightly longer than intended.
It's fine.
So what have I written here? Some gobbledygook. So the pi system for Y would be, so remember pi system for R. We defined a pi system for R, remember? In problem sheet 1 and in lecture 1.
Yes.
So if you remember that, this should just be the inverse image for all the sets in pi system. But if you don't remember that, then that is also fine. You can use this definition. So what is this telling us? So all this is telling us is that, so if x is less than or equal to x and y is less than or equal to y, equals p of x less than or equal to x times p of y less than or equal to y, then x and y are independent. Does that make sense? If there's any question, then do ask me because everyone's so silent. Okay, so these are the pi systems for x, and what we are showing is that this limit at and. So what we are showing, and is the intersection. So what we are showing is that, so if these pi systems are independent, then the sigma algebras which are generated by those pi systems are also independent.
Wait, is that like a joint distribution?
Yeah, you could say that's like a joint distribution. If I said comma, if I said intersection, then you could say it's just intersection of two different things. Yeah, but you're right.
Same thing. Yeah.
Yeah. Okay, so if you guys want to remember only one thing from today, then make it this one. So that's going to be the all-powerful.
Cantelli. Ooh.
Yeah. So remember we had one Borel-Cantelli lemma in the last lecture. This is known as Borel-Cantelli lemma 2. Okay, could anyone tell me the statement of Borel-Cantelli lemma 1?
Let me look that up.
Yeah, we'll be using this so often that I'm going to write that BC2.
Okay.
So what this tells is that, so if En, don't worry if you don't remember that. I'm going to tell that one as well in a moment.
Okay.
So suppose this is a sequence of events. Then BC1 tells, so if the probability of En is less than infinity, that means it converges, then probability of En infinitely often, or limps up if you like that one, is equal to 0. BC2 assumes further that EIs are independent. In that case, if it actually is infinity, then that implies that P of En infinitely often equals 1, which is also, if you remember limit supremum and limit infimums from analysis, that's going to be lim sub of En. So P of lim sub of En.
Oh wait, so BC2 is like the case, the special case when the sum is okay.
It's not, those two are independent cases, but they are related because one deals with infinity and other deals with non-infinity
Finite.
variables.
Okay, yeah, but that's why they're all called Borel-Cantelli. Okay.
Yeah. The proof is pretty simple. Oh, okay. Okay, I'm going to use a couple of more minutes. Should I prove this or give you guys an example of application of Borel-Cantelli lemma?
Application.
Okay, application. Okay, so proof, look in the book.
Sure.
Yeah, I'll give you guys an application. Okay, suppose you've got a sequence xn, sequence of independent random variables. I would like to use IID, independent and identically distributed, but I haven't defined that. Variables such that. So P of xn greater than x equals e to the power minus x greater than 0. You might recognize this as the exponential distribution. Okay, then the question is, what is the probability So what is the probability that what is the probability that xn is greater than alpha times log n, given alpha positive, alpha greater than 0, is greater than log n for infinitely many n? Okay, before I prove this, could anyone tell me, would this be provable using only the techniques that we have developed in our first year?
No.
I'm not sure. I think it's not possible, but someone could correct me on that if they manage to find a proof without using any of these Borel-Cantelli lemmas.
Yeah, I think it's definitely out of the scope of what we've done so far.
Yeah. Okay, but the probability, so what we are trying to do is for how many random variables is xn greater than x log n? The only information we know is that they all follow exponential distribution. So this is the probability about exponential distribution. So previously we were using probability to calculate exponential distribution. Now we're using probability to find out which exponential distribution follow these kind of things. How many of them?
Okay, so that would be.
So xn greater than alpha times log n.
All right. Okay.
Would be n to the power minus alpha, right?
Yeah.
Yeah. And we all know, you should have bread and butter by now, that. So when I say bread and butter, I mean really simple things. So the zeta function defined to be n equals 1 to infinity of 1 over n to the power of s converges if the real part of s is greater than 1. Does that make sense?
Wait,
Where s could be real or complex, but we'll
Okay,
be
yeah.
only be dealing with real numbers here.
Yeah. Converges if the real part. Yes, that's true. Oh, and
Yeah.
then DC2. Oh, right. Nice. Okay.
Yeah. Okay. Then what I say, so if I apply, so for alpha greater than 1, what is sum of probability of xn greater than alpha log n? That would be sum of n equals 1 to infinity of n to the power minus alpha. This is less than infinity, right?
Yeah.
Because this converges. So since it converges, then BC1 applies.
Right.
So by BC1, probability of xn greater than alpha log n for infinitely many n equals 0, right? But when alpha is less than 1, less than or equal to 1, then this is divergent. Then BC2 applies because the random variables we have taken are independent. So by BC2, the probability is going to be 1.
Nice.
Okay, so that's it for today. The problem sheet is going to be out in a couple of hours. Thank you for joining us.
Thanks.